Hello and welcome to this video introduction to ShowWhy, an open source application for Microsoft Research that aims to make causal decision making accessible to anyone with a causal question and access to relevant data. It does this by guiding the user through the end-to-end process of modeling domain knowledge, estimating causal effect sizes, and validating these using sensitivity analysis. ShowWhy currently supports 3 causal tasks linked to 3 types of causal question, all of which can be answered using observational data already collected and available for analysis. First, causal discovery. How do the features in a dataset appear to cause one another? This is useful for exploratory analysis seeking to discover causal hypotheses. Second, exposure analysis. Does a specific exposure appear to cause a specific outcome? This is designed for confirmatory analysis looking to develop evidence in support of the existence and strength of a single causal relationship. Third, event analysis. Did a specific event cause a specific outcome? This kind of analysis requires longitudinal observations of multiple units before and after some were exposed to the event in question, and allows for the construction of appropriate control groups. Now let's look at each of these causal tasks in the context of examples related to smoking. You can see that this has loaded a variety of saved datasets, including this NHEFS dataset on a national health epidemiological follow-on study. Since data typically needs some degree of preparation before it can be analysed, ShowWhy includes a wide range of data transformation capabilities. These include column-based transformations like bin, binarize, filter, aggregate, and so on, as well as multi-column table-based transformations like join, lookup, and so on. For example, if we wanted to bin the age column of this dataset, transforming it from continuous integer values to a smaller set of discrete age ranges, we simply select the target column, an operation, name the column, and save. If we scroll, we can see the new column added to the dataset. In this example, you can see that the same dataset has been prepared differently for exposure analysis and causal discovery respectively. Let's move on now to the task of causal discovery, which has the NHEFS discovery table preloaded. Imagine we're interested in whether quitting smoking causes weight gain and how this might vary by age and gender. We can add these variables to the canvas. Select Layout to view the correlations between these variables, shown as grey lines. Select Discover to detect candidate causal relationships using the selected discovery algorithm. And then Layout again to see the results, with positive causal relationships shown in green and negative relationships shown in red. Here we see that age has been misdetected as the effect of other variables. We can remove these edges and rerun the discovery algorithm to get a new graph that we can view in a new layout. The same process can be repeated to properly assign sex as a causing variable. Now we see that quitting smoking, QSMOK, has a positive causal impact on weight gain from 1971 to 1982. And quitting smoking is itself caused by age and sex, being more likely for older females. Interestingly, these variables otherwise cause weight gain to decrease, as shown by the red lines. By selecting our outcome of interest, in this case weight gain, we can also discover correlated variables to add to the analysis. We see that both smoking years and weight in 1971 are highly correlated. And after adding these variables to the analysis, we observe the same result. To take the analysis further, the Deep End-to-End Causal Inference approach, or DeSi, could discover nonlinear causal relationships in even high-dimensional datasets, using the latest advances in deep causal learning. DeSi exposes a rich array of parameters for customized training, modeling, and effect inference. It also allows us to consider an outcome of interest, say weight gain, and observe the estimated effect of intervening on its causes. What we can see here is that 26% of subjects in the dataset quit smoking. If instead everyone in the dataset were to quit smoking, the average weight gain would increase by 0.65 standard deviations. And if no one in the dataset were to have quit smoking, then the average weight gain would decrease by 0.24 standard deviations. This ability to perform what-if simulation is an incredibly powerful way to explore counterfactual worlds that could have been, especially as a way to learn more about the interventions that should be taken to create a more desirable world in the future. Next, let's imagine we already have reason to believe that quitting smoking causes weight gain, and we want to evaluate this hypothesis more rigorously. This is where the exposure analysis workflow comes in. In the preloaded example, we can already see this question framing our analysis. What we are asking is, for the population of cigarette smokers, does exposure to smoking reduction cause the outcome of body weight change to increase? Note that in this workflow, we need to define our question and build our causal model before we know what data we need to collect and how to transform it in order to estimate causal effects. There may also be multiple ways in which we can define the various elements of our causal question. For example, here our primary definition of smoking reduction is quit smoking, but we also want to test the sensitivity of the estimated effects to different levels of smoking reduction than 100%. Next, we build a causal model of our domain knowledge. We can see our hypothesis at the bottom that exposure to smoking reduction causes the outcome of body weight change. However, if we only consider these two variables in the context of observational data, we're likely to get a biased result. This is because the exposure was not randomly assigned to individuals by an experiment, A/B test, or randomized control trial. Therefore, other factors may have caused it to be observed in the dataset. If these same factors also cause the outcome, then it becomes impossible to isolate the causal impact of the exposure on the outcome without controlling for these confounding factors. To build this domain model, the user is asked to consider all causally relevant variables, as well as their relationship to both the exposure and outcome. Different evaluations as to the strength of these hypothesized relationships allow the creation of different causal models for different degrees of belief. Next, data must be collected and transformed to represent all of these model variables, as well as alternative definitions of population, exposure, and outcome. This is the work done in the NHEFS exposure dataset, visible here as 10 workflow steps, including deriving a new column representing smoking intensity change and binarizing it against different threshold values to create alternative exposure definitions. Back to the exposure analysis in progress now and the bind data page. Here, the user binds the columns of their dataset to the various elements of the causal question and causal model. We can see that all 16 such variables have already been assigned, so we're ready to move on to the final page and estimate causal effects. And it is multiple causal effects that we're estimating, rather than a single effect size, since we would like to analyze the sensitivity of our estimates to changes in the specification of the analysis. We've already specified alternative exposure definitions and causal models, and now here we can select a range of alternative estimators used to estimate the causal effect. We can also specify how many simulations we'd like to run for each of several refutation methods designed to test the robustness of estimates against violations of their underlying assumptions. The overall idea here is that if we get the same clear result for all specifications of the analysis with estimates that are robust to violations of their assumptions, we can be much more confident in that overall result. And if not, it gives us necessary caution when interpreting individual results. Let's now begin estimating these causal effects across 28 different specifications of our analysis. We can see that each individual estimate appears as soon as it's available, with estimates ordered by ascending effect size. Once this process is completed, we can view more details on each estimate. Our primary specification is shown here in bold, and it also has the highest effect size out of all estimates. This was obtained using the maximal causal model, the linear doubly robust learner estimator, and the quit smoking definition of smoking reduction. We can also check confidence intervals if they've been computed, as well as look at how each element of the analysis specification contributed to the overall effect size. Here we can see that the model, estimator, and exposure definition all made a positive contribution to the primary effect estimate. A benefit of this overall approach, of course, is that it isn't necessary to rely on a single result. Instead, we can perform a statistical significance test over all candidate estimates. This means first rejecting any of the computed estimates that appear problematic, for example having excessively large confidence intervals or having been computed with an unadjusted causal model known to be wrong. We can then run a final significance test against the remaining specification curve to obtain an overall answer to our causal question. And in this case, the answer is yes. for cigarette smokers, smoking reduction does indeed appear to cause body weight change to increase. Now, sometimes we have causal questions not about whether an exposure causes an outcome in general, but whether a specific event caused a specific outcome of interest. And this is where event analysis comes in. Here, we're looking at the causal impact of Proposition 99, legislation introduced in California in 1989 that added a 25% tax to tobacco sales. The causal question here is whether for the treated US state of California, did Prop 99 cause cigarette sales to decrease? We can see how this question might be hard to answer in the context of falling cigarette sales overall in the years before and after 1989, not just in California, shown here as the blue line, but in all US states. However, it's still possible to estimate the causal effect of Prop 99 by constructing an appropriate control group from other states that mimics the behaviour of California in the pre-treatment period up to 1989. If the behaviour of California diverges from this control group after the treatment, we can then reason that the difference was caused by the event itself. There are multiple ways of constructing this control group. Here, we're going to use the synthetic diff and diff estimator to calculate our causal estimate. We can see here how the behaviour of California compares to that of a synthetic California composed from a control group of 18 other states, selected and weighted to precisely follow the behaviour of California in the pre-treatment period. After the introduction of Prop 99, however, we can see that cigarette sales in California drop faster than in synthetic California. We can see this even more clearly if we align the curves pre-treatment, and even more clearly still if we plot the difference between California in blue and its synthetic control in green. This overall treatment effect is estimated as a reduction of 15.4 cigarette pack sales per capita. We might reasonably ask the question, though, as to whether we might have seen similar or even stronger effects had we run the same estimation process for other US states. This is called placebo analysis and is the main way in which we can attempt to validate our effect estimates. By running a placebo unit comparison, we can see how this difference in outcome visualization for the actual treated unit of California compares to the same plots for other placebo units that were not subject to Prop 99. We can also compute a ratio that captures the extent of post-treatment divergence from a well-fitted control group in the pre-treatment period. Here, we see that California indeed has the largest such ratio, increasing support for the conclusion that Prop 99 was the cause of this decrease. A statistical significance test also gives an exact p-value that represents a significant result at the 5% level and can allow us to say with confidence that yes, for the treated US state of California, Prop 99 did indeed cause cigarette sales to decrease. This concludes our video introduction to ShowWhy, a collection of no-code interfaces that aim to make causal decision-making accessible to everyone.